We are all aware that the world today is faced with a problem of human population increase, and recently we hit the 8 billion mark. Fresh water is one of the most vital needs for human life, but it's seemingly not enough due to this increased population of people across the globe. Shall we find alternative water sources, especially fresh water sources? How best can we ensure that the human race is supplied with adequate fresh water? My name is Oscar Kayanja, pursuing a master's degree in material science and engineering from Egypt Japan University of Science and Technology. And in this work, we try to employ a novel approach to modify a polymeric membrane made of polyether sulfone, with modifying it with molybdenum disulfide nanosheets and targeting wastewater recycling, and this wastewater treatment targeting particularly oily wastewater. How unique was this study? Did we surely achieve reliable and realistic performance indicators? Follow me very closely. We shall be looking at the background and aim of the work, the approach we used to prepare molybdenum disulfide nanosheets, the preparation process of fabricating the polyether sulfone nanocomposite membrane embedded with molybdenum disulfide nanosheets, the performance parameters for the resultant nanocomposite membrane, conclusions, and future work. Well, there are several sources of oily wastewater, and one of the main being industrial effluents. And sometimes there is always oil spills in our open water bodies, especially from vessels carrying oils. And when this oil finds its way in open water bodies, it cuts off oxygen supply, and this negatively affects aquatic life. It creates a poor scenery, it contaminates the entire ecosystem, and actually it results in the death of the fish. There are several ways through which oily wastewater has been treated, and in this includes conventional techniques, for instance, flotation methods, coagulation processes, biodegradation, as well as adsorption processes. But there are also advanced techniques, among which includes membrane technologies. Membrane technologies have actually been better than conventional methods due to the simplicity of operation, as well as use of cheap materials and being compact. But they have a limitation of fouling, whereby the contaminants in the wastewater block the water channels, and hence researchers have decided to embed nanoparticles in membranes to enhance their properties. Of course, when nanoparticles are embedded in membranes, they create electrostatic attraction, which creates additional diffusion paths. Some nanoparticles are hydrophilic in nature and hence increase the water mobility. Some nanoparticles also change the viscosity of the casting solution, and which enhances the porosity of the membrane, and also they have been found to induce anti-fouling properties. We have found out that molybdenum disulfide nanosheets can actually exist in different phases, but remaining the same material, that is molybdenum disulfide. And hence in this work, we would like to study the effect of having these different phases of molybdenum disulfide, and then how do they affect the performance of the resultant isotropic polyether sulfone membrane when these nanosheets are embedded in the polymeric membrane. So we divided this work into 3 work packages. The first one being the preparation of the nanosheets themselves, secondly being the preparation and characterization of the resultant nanocomposite membrane, and then thirdly, checking the performance of the resultant nanocomposite membrane. For the first work package, we started with blending ammonium molybdate, which was the source of our molybdenum, and thiourea, which was the source of sulfur, with water, with the ionized water, and then used the hydrothermal technique or the hydrothermal cell to heat. We heated it at 200 degrees Celsius for 24 hours to form mixed phase molybdenum disulfide. And mixed phase, this molybdenum disulfide prepared in this way had a 70% of 1T phase, in the 2H phase. And further processing involved drying of this black powder, and if we could extend the processing by heating this powder at 800 degrees Celsius for 2 hours, the resultant was the single phase 2H molybdenum disulfide nanosheets. And characterization using the scanning electron microscope revealed the flower-like structure of molybdenum disulfide, and this is typical for molybdenum disulfide according to other literature. Observation under the transmission electron microscope showed thin petals of molybdenum disulfide, and obtaining a high-resolution images revealed a d-spacing of 0.22 nanometers for all samples. The distinction of molybdenum disulfide nanosheets prepared were clear with ultraviolet spectrophotometer characterization, whereby for the mixed phase molybdenum disulfide, it just had a smooth curve, whereas for the single phase 2H molybdenum disulfide, it had these two characteristic peaks at this location, typical for the excitation in the Brillouin K zone at the K point of the 2H phase. The suspensions, of course, were a dark blue suspension for the mixed phase molybdenum disulfide, whereas a dark green suspension for the 2H phase. And of course, using an avometer, the electrical resistance for the two powders were also different. We therefore went ahead to blend these powders with polyether sulfone in addition to other additives. For instance, the NMP was used as the solvent, whereas PVP was used as the pore former. And the solutions were very viscous, so we took beyond 3 days of mixing. After the mixing phase and achieving a homogeneous blended solution, we degassed the solutions using a vacuum oven and casted the solutions using a casting machine, which was having a humidifier to achieve a proper isotropic membrane. And these were the blending weight percentages. FTIR characterization revealed all functional groups typical for polyether sulfone. And the addition of molybdenum disulfide in polyether sulfone actually did not affect much the positions of the functional groups. And also using a thermogravimetric analysis, we realized that the decomposition temperature of polyether sulfone was also not much altered. The mixed phase molybdenum disulfide nanosheets made the resultant polyether sulfone and composite membrane hydrophilic, as evidenced by the low contact angle, and the single phase actually made the membrane hydrophobic. And this actually affected the pure water permeance, whereby the mixed phase had a higher pure water permeance, whereas the one for single phase molybdenum disulfide blended with polyether sulfone had a very low water permeance. The permeance of different concentrations of synthetic oily wastewater were different, and as can be seen, for 0.1 gram per liter, it had a higher permeance as compared to the 10 grams per liter. And we checked the membranes for different cycles, and for each cycle, pure water came out of the membranes. We checked the performance of membranes, of the prepared membranes, over 3 complete cycles. We started with using pure water, then subjecting the membrane material to oily wastewater, and use pure water again, subject the membrane material, or use oily wastewater again, use pure water and use oily wastewater again for the 3rd cycle. And we did this using 3 oil concentrations for the 3 membrane samples prepared. And as can be observed, this is for the unmodified membrane. Its performance was relatively around, the pure water permeance dropped from around 5,000 to around 4,000, whereas for the hydrophilic membrane, its performance, pure water permeance, was relatively high for the for the low concentration oily wastewater. And as can be observed, the hydrophobic membrane had a stable performance, but of course it had a low pure water permeance. And we also performed a chemical oxygen demand analysis to check for the carbon content in the feed as well as permeate solutions. And as can be observed, the rejection performance was very good for the hydrophilic membrane, and it was very poor for the hydrophobic membrane. This can be linked to the relationship between hydrophobicity and oleophobicity, the love for oil. When the membrane is hydrophobic, it is oleophilic, which means it's easy for oil to cross through such kind of membrane which is hydrophobic, and which was not the case for the hydrophilic membrane, which had a very good oil rejection. And therefore, we successfully prepared molybdenum disulfide nanosheets, which revealed a flower-like structure under scanning electron microscope, and it was distinguished by UV spectrophotometer, as well as had different resistance characteristics. We blended the nanosheets into polyether sulfone and fabricated resultant isotropic membranes, which had different performance characteristics. The optimal membrane actually had a high rejection performance towards oil for an oil in water emulsion. In the future, we also intend to use these membranes to study how they can reject other organic foulants, and we shall also study the fouling behavior of these membranes to actually find the effect of molybdenum disulfide on the fouling parameters. I cannot end this without thanking the research team comprised of my supervisors, as well as my lab engineer, as well as our JICA funders, funding us through the EJAS TICAD 7 African Scholarship for Science, Technology, and Innovation. Instead of looking at oily wastewater as a problem, we have decided to look at it as an opportune source of water that can be used for domestic and industrial applications. As stated in the beginning, due to the growing population of people around the globe, there is a growing need for sustainable and reliable sources of water that should meet the global demands. And the question is, are we realistically achieving this through extensive, creative, and innovative research? Thank you very much.